Gosh. Hi, everybody. Okay, so we're on chapter 14, which is energy. This we've been kind of talking about a little bit in terms of the simple machines and how they help us maybe be more efficient and those kinds of things. But now, so this is just about energy itself. So first thing to do is define energy, and it's a little bit hard to define. The technical definition is that it's the ability to do work. Energy is not something that like I can say, here is energy. Like I can't show it to you. I can't, it's not like I can say, hey, this is a first class lever. I can't do that with energy because really we don't have a good definition for it, or we can't really know what it is, but we know the result of it. So we know it's the ability to do work. We also know that energy is what holds all forms of matter together. Albert Einstein was the person who related the two with his equation E equals mc squared. He also, as part of that, said that matter and energy are interconvertible, which means you can convert them into each other, which is what his equation tells us. So anyway, so it's kind of a vague kind of thing, but it is it's big in terms of what God created and how we can use it. Okay, so a little bit more practical stuff. Energy, when we do some of our math, is measured in joules, so that's the unit that you're going to use. It also is something to be aware of is that energy can be converted into different forms of energy. So like, and we're all familiar with a lot of these, even though we don't really think about it, like solar energy from the sun can be converted into electrical energy in our homes. And here's the deal with energy. Just like matter, it is never created or destroyed. It can only change forms or be transformed from one thing to the other. We have never created energy. We've never destroyed energy. We've only changed it from one thing to another because we're in a closed system. So we can't change that total amount in any way. And so it's a constant, which is going to give us some different ways to use the equations that we have for energy, and just some kind of different values. Okay, so first major form of energy is kinetic energy, and this is energy that objects have due to their motion. And so are they moving? And the amount of energy actually depends on how fast the object is going, and then also the mass of the object. So it's so how much matter it is made up of. And so if we know the kinetic energy of the object, we can have some way to determine its ability to do work. And we'll talk about it more in class, but I've got two different hammers there on the screen. And just to be thinking about, like which one do you think would do more work in general? So if you're trying to smash something, for instance, which one's going to do a better job? Why? Could we possibly make these two different tools do the same amount of work? How would that happen? All those kinds of things. So it's just kind of something to think about. And as far as, practical use, it's something that engineers have to think about all the time, something that someone who is working with those kinds of tools. What's the right tool for this job? How much force do I want to put behind it? What am I trying to accomplish? A lot of this is going to be kind of, again, common sense in a way to us. Like obviously looking at those pictures, which hammer is going to do more work, but there's a reason behind it. Okay, so now calculating kinetic energy, here is the formula that we will use. So this will be, like the one that we'll put on our note card. Okay, my pen's not, there it goes. That we will put on our note card. It is 1/2 times the mass of the object times the velocity squared. And so mass will be measured in kilograms, velocity is meters per second. And if you think back to some of the units that we have converted and done all those kinds of things for, this converts back into Newton meters. It also converts back into joules. And so anyway, so the units thing just kind of keep that in mind. Anyway, there are a couple of examples that we will do together. You're welcome to look at them. Very straightforward. This is algebra type problems, so it's maybe moving things around to solve for x, but it's not math that you haven't done before. So don't be scared about it. Okay. All right, another example. We're going to calculate this one too, but of course feel free to do it ahead of time. Okay, so now transferring energy. So remember, it's always conserved when it's transferred or transformed. Okay, so we always have the same amount of energy. This concept is what helps us predict. Okay, if I change the motion of another object, if I hit it with something else, how is its motion going to change? So how is its energy going to change? So the example question on this page is about a baseball bat, and it has a certain amount of energy, of course, that it is moving with as the batter swings it. If it hits the baseball, assuming no energy is lost, which is, an assumption that we have to make just to work this problem, how fast will the ball move after it is hit? And so again, kind of a common or a useful application, if you're trying to engineer something, make some sort of tool or that kind of thing. Okay, so now our other big form of energy is potential energy. So this is the energy of condition or the energy of position. And essentially it is stored energy that will be used later as kinetic energy. And so the book uses a couple of different examples. So you have something, for example, like elastic potential energy. So when you pull back a rubber band, to shoot it at someone, which never do that. But if you do that, that stretched rubber band has elastic potential energy. When you let it go, when you shoot it at someone, that energy then is being used and it is now moving, the object is now moving, the rubber band, and so now it has been transformed to kinetic energy. Chemical potential energy, there's several of these, but I chose one most relevant to us, is what is stored in foods. So food that we eat, it has energy in it, energy that's holding that matter together. And when our cells actually use it, when they go through all the processes to break that food down during cellular respiration, then we have the ability for our muscles to move or our heart to beat or whatever it is. So that energy that has been stored then is transferred into some sort of motion, some sort of kinetic energy. It goes on all the time. And so there are lots of different examples. We'll talk about some more in class, but be thinking kind of about the different forms. Okay, so now one big form of potential energy is gravitational potential energy, and this one is energy due to position, and so it's energy that is done or is due to gravity's work on an object as it falls. And so I can increase potential gravitational potential energy by putting an object up higher, on a shelf or whatever it is, or by increasing the mass of the object. And so I've got my question there, and again, this is something which would you rather have fall on your foot? The sledgehammer from a couple pages ago, the toy hammer, why? And obviously you've got some common sense, but that mostly will have to do with the mass. But anyway, we can calculate gravitational potential energy. That should be an equal sign right there. My pen's not going to work again, so that's fantastic. Okay, there we go. So that should actually say equals. What is happening? Sorry. Okay, scribble, scribble. Are you working? All right, well anyway, here is our equation. Gravitational potential energy equals mass times a gravitational acceleration constant, which is familiar to you, and then the height of the object in meters. And again, if you work out all the units, all that kind of stuff, you could have kilograms times meter squared over seconds squared, which converts to newtons times meter, which converts to joules. So anyway, those conversions are all kind of there. But again, basically you'll be given some of those components and you'll be asked to find the other parts of that equation or find the answer. All right, so here are a couple of examples. Again, feel free to do them, feel free to wait, but we'll go through them together and just show you some of the math involved. Okay, so here we are. So, second part of chapter 14 is mechanical energy, or starts with mechanical energy. Mechanical energy is the sum of any kinetic energy, so motion, and then all forms of potential energy. And so this picture is not necessarily the most common one to represent these energy transformations, but I think it's a pretty good one. And so if you'll look at it just for a second, here you've got this wagon or whatever that thing is, and it is down at the bottom of a hill, which means that it has no potential energy. Height has none. Other conditions we don't really know because it's just moving, but it has a ton of kinetic energy, which means it is in motion. We can't really tell because it's just a drawing. But then so it will go up the hill. When it gets up to the hill, there's a pause. There, you get to kind of get to the top. And then it goes on. But that pause at the top means no kinetic energy, no motion. But because it is so high up, tons of potential energy. And then as it goes down, it's kind of, halfway down or so, it's moving. So there's kinetic energy. It's still got some height. So there's potential energy. And so you have this kind of constant shift where it all still equals the same amount if you added all the parts up, but it is kind of varying depending on what's happening, where it's going. We'll talk about it in class, but if you're listening to this, think about a swing. Think about how, if you've ever been on a really good swing and you've gone really, really high, you're constantly transforming the amount of energy that you have from kinetic to potential and kind of everywhere in between. So anyway, it's a concept that we're all kind of constantly kind of going through. Okay, so these energy transformations, so energy, like I said before, is constantly changing from one form to another. So we've been talking about kinetic and potential, but it can also be very specific forms of energy, electrical energy, light energy, heat energy. So like a light bulb transforms electrical energy that comes in through the cord, after you have plugged it in. And that light bulb then gives off light, which is a form of energy. And it also, if you've ever gotten real close to a light bulb that's been on for a while, it's hot. So you have some heat that has been produced. A car engine takes chemical energy in the form of gasoline. As it is broken down, it is converted into a form of mechanical energy, motion, the different parts of the engine move, all that kind of stuff. So things that we have built, like people, man-made stuff, typically don't do a great job of transforming the energy efficiently. We tend to lose energy, or it ends up being called lost energy or unusable energy. We really typically only get between 20 and 40% of the actual energy out. And so we'll talk about it, but just kind of a little precursor, it has a lot to do with some of the other things that we've talked about in terms of loss. So think about things like friction and those kinds of things. And what form of energy would we be losing if that is produced, if heat is produced? Okay, so now last part. So some energy resources. So how do we generate energy? What stuff are we using? What are we transforming to get energy that is usable for us? And so we have non-renewable energy, which I'll get to kind of at the end, and then renewable. Renewable energy is the stuff that is easily replaced by natural methods. And so on that little graph there, the darker green is the renewable. And so this is stuff like wind, because wind is always blowing, or hydroelectric has to do with water, biomass, or things like plants. So if it's being replaced because it's still growing or still moving or still whatever, then it's renewable. Non-renewable are things that are not replaced naturally or that are not replaced in a timely manner. And so that's what we're going to talk about first. And I've got some listed on that picture there. We're all super familiar with these. And we're going to talk about the first one is fossil fuels. So fossil fuels are formed by the remains of plants and animals, things that lived in the distant past. Depending on who you talk to about it, a Christian, I do, believe that these fossil fuels were were laid down or were put in place during the flood. Other people, evolutionists, those kind of things will think it's just kind of a time frame kind of an issue. But anyway, plants and animals that have been buried in sediment and compressed and lots of heat and all that kind of stuff become fossil fuels. We can use fossil fuels directly, like we can burn them, or typically we can also use them and transform by burning or some other motion, transform them, into electricity. There's lots of benefits to these fossil fuels. Kind of depends on your opinion right now with all the costs of things, but they're considered inexpensive, fairly abundant, although we need to be concerned about their amount. A fairly high usable energy content. So the energy that's in there, we get a lot of it out. We know how to use it, like the current technology that we have, like it works. Some of the problems, air pollution is a big one because you burn these. Extracting fossil fuels from the ground can be pretty harmful. You can really destroy a lot of the surface to get to the things that are underneath. We do have a limited amount. We do think that we could run out of these, and so you're hearing more and more about people, like electric cars or these renewable energy sources because of the worry about running out of these fossil fuels. Okay, now we also use nuclear energy, and so this is energy that is produced by nuclear fission reactions. So fission means that two things split apart, and in this case it is an atom being split apart. And we haven't talked about it a lot. We actually skipped over this chapter just so we could kind of keep things moving. We'll talk about it a little bit more, but basically you smash two atoms together, and if you smash them together correctly, and I know I'm really simplifying it, they break apart and release tons of energy. Then that energy is used to heat water into steam. That steam turns like a turbine. That turbine is a generator basically that produces electricity. France, almost all of their energy is produced through nuclear energy. We kind of, depending on the parts of the country that you live in, have some nuclear power plants. The East Coast has some. There's some along certain rivers. I haven't looked into it in terms of Oklahoma. We're more in the fossil fuels just because of where we live. But kind of depends on the country. And there are some definite benefits. It produces a lot of energy from a very small unit or amount of fuel. There's one tremendously big problem, though, is that when that fuel is used up, it produces very radioactive waste, like radioactive to the point like it is dangerous to people. And so anyway, so that's huge issue. And you may have heard of some issues with nuclear power, some meltdowns of different places. We'll talk about some in class, but so this is an energy source that is being used, but it's also, we're all still kind of a little like we wouldn't want a nuclear power plant in our backyard. Hang on. Okay, so now renewable energy. I've got 6 listed on here, so we're done. So these are the things that can be renewed either daily just because of conditions, or we can plant them, or So biomass energy is the first one. This is the chemical potential energy in these renewable organic materials like wood. So cutting down a tree and burning it, that's biomass energy. Hydroelectric energy, this is energy generated by the movement of water. So if you set up a power plant, like on a river, as the river runs, it turns big, wheels, basically. Those wheels generate electricity. Geothermal energy is heat energy from within the earth. So we can use that, harvest it, and then again, kind of convert it. Solar energy, we're pretty familiar with that one. You have solar panels that can convert light energy from the sun into electricity, into heat. Wind energy, another one that we're pretty familiar with. If you've driven, between Pawhuska and Ponca City, you've seen the wind farms. So you have big, big windmills, and as the blades turn, they generate, they're turning, and they're part of a generator system that produces electricity. So again, renewable, because hello, it's Oklahoma, the wind blows. Tidal energy, if you're on a coast, the rise and fall of the tides can move turbines. So similar to hydroelectric energy in terms of what's happening. Anyway, these are all renewable. These are all sources that we are still kind of investigating. The benefits, of course, is they're renewable. Like, we're not going to run out of these. There is some concern, of course, about, the deforestation and all that, but we do have people replanting and trying to keep it kind of where it needs to be. I have clean on my list there in quotation marks. It does produce some, it does produce smoke and those kinds of things if you burn a tree, but it is, less harmful than burning a fossil fuel. But some concerns is they don't seem to produce, like, we don't get as much energy out. And so we have to burn more, or, we have to just settle for less energy. And so that's an issue. There are environmental issues with some of these renewable energy sources. The big one that comes to mind is the wind energy, just I think because it's the most recent. The big giant windmills are great, but they're detrimental to birds. And to the farm, to the land doesn't, you have to have pretty big amounts of land to to put up your windmills. So anyway, so there's all kinds of issues that are associated with that. But essentially, energy, we've got it. We just need to know how to use it well. In terms of our renewable energy sources and even our non-renewable energy sources, the big thing is wise usage. And so conservation of energy is something that more and more of us need to kind of work at and, kind of deal with in a way that's really beneficial to everybody. Okay, that's all I got. Bye.